Hi, in this video we will be learning how to run simulations for multi-input gate, something like AOI 222. So the circuit diagram just looks like this, and the symbol is this one. So basically you have three AND gates. So each with a two input, and then the output of all the three AND gates is ORed. Then and the output of that OR gate is then given to and not gate. So AOI, that is why it's called AOI. Okay, so we shall see how we will be providing or forcing the input signals, right? So generally what we will do, earlier we had done simulation for NOT gate. NOT gate was just we had one input and we were giving pulse waveform like this, and we were getting the inverted output like this. Okay, so now we have multiple inputs. So if you consider table, then if there are like two inputs, if you have to see for all the input combinations, for two inputs it will be four combinations, right? 0 0 0 1 1 0 1 1. So here you will be evaluating the expression for all the input combinations, and then closing the truth table. For similarly for three inputs it will be eight combinations. So here we have six inputs. Okay, so six inputs means 2 power 6, that is 32 64 combinations, right? 2 power 5 is 32 and 2 power 6 is 64. Okay, so 64 input combinations. In one simulation run you will be able to evaluate the schematic. You will be able to see all possible combinations for all input possible combinations. You will be able to evaluate the output. You should be able to do that in one simulation. You should not be providing some input data and running simulation, give 0 0 0 all 0 and then see output. That should not be the case. In one simulation run you should be able to provide all the input combinations, and the corresponding output waveform should be present. So how I am telling is, so if you consider this is your gate, right? um, AOI 222. So let us name it let us name the input according to the circuit diagram only. So we have 101120. Okay, so you have V in 1 10 11 20 21 30 31. So these are all input uh, terminal names. Okay, so now we have input terminals name like this. This is my LSB and this is my MSB bit. So if you see that here three zeros, and it will be going from all ones. So if you actually see MSB, it will be four zeros, right, and four ones. And similarly here two zeros, two ones, two zeros, two ones, and 0 1 0 1 0 1 0 1. So it will be like this. So if you actually see draw the waveform for this, it will just look like this. Right? So all 0, then 0 0 1, then 0 1 0, then 0 1 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1. So for, this is for three input combinations. So what about if you have four input? So you will be having this repetition entirely again for one more cycle. Okay, and your output will be I mean sorry, MSB fourth if you have four input combinations, I'm saying. So like this it will be. So one when it is entirely zero for all the eight times, and entirely for next eight combinations it will be one, and then you have all these waveforms getting repeated. And similarly five inputs, it will be this thing will get repeated here. Okay, so same thing goes for six also. How you will be giving this in your how you will be providing these input signals in the ADE L window, that we will see. So just before that we should also try to understand one more thing here. So if I have to tell in terms of period, so what is happening, you just try to understand. Say I have my period for LSB as 10 nano. Okay, so let us assume 50% duty cycle. So 50% of the time means 5 nano, it will be 0, and for 5 nano it will be um, up logic high. Okay, so totally the period of LSB is 10 nano. Then the period of the next bit of the LSB, next higher bit of the LSB is what? It will be 20 nano. Then it will be having double than that, 40 nano. Then it will be 80 nano. Then it will be 160 nano for fifth bit, and similarly 320 nano for sixth bit, right? So from LSB, I'll just write what should be the wave this thing period for the waveforms that are given to these inputs. I'll just one more time I'll write V in 313021201110 Wien. So let us assume this has a 10 nano period. This will be 20 nano. This will be 40 nano. This will be 80 nano, 160 nano, and 320 nano. This is time period for these inputs. We will be giving pulse as the pulse data type, right? Pulse data type will be our input data type for all these inputs that we will be providing in ADL window. We'll see now how it works actually. So first you have to launch ADE L for that, and then uh, we have to first go for transient simulation. So we have to give the stop time, right? So uh, what is the period of the MSB will be our stop time. So what I will do is generally I will give some 5 nano or 10 nanoseconds more than the period of the MSB. So if it should be actually like 320, I should be giving instead of 320, I will just give 325 just to ensure that it is properly going down at the edges. Also, I need to verify the waveforms here also. So I will be just providing 5 nanoseconds extra for that. So I will be providing instead of 320, I will be giving 325 nano, and then I'll give it moderate and then click OK. So then let us take outputs to be plotted, select on design. Um, so all the inputs I will be selecting, and then I'll also select the outputs. I'll just arrange them in here properly. Okay, 31302120. Okay, 1110. I just wanted to arrange it properly like MSB to LSB, and then I'll check the model libraries. So it is CDS FFmpt proper. Model libraries is perfect. Then what else I need to provide the stimuli now. So first we'll deal with VDD. We will be keeping the function or data type is voltage, of course, and the function is DC, and it is zero point 0.8 volt for this technology. And for VSS, we'll give 0 volt, right? It is nothing but ground. And then we'll start giving from input V10, which is our LSB. So pulse I will give, and voltage 1 I will give it as um, 0 0.8. Okay, and voltage 2 is my 0, and period will be 10 nano. Okay, so then delay rise time I will keep it 50 pico, fall time also 50 pico, pulse width I will give it as 5 nano, and delay time I won't be providing any delay time, and I'll just click on apply. Similarly I'll do it for V11. This will be period will be 20 nano, double than the V10. and 50 pico, rise time 50 pico, fall time, pulse width will be 10 nano because 50% of the duty cycle, right? So there we had 5 nano pulse width and 10 nano was the period. Here 20 nano is the period and 10 nano is the pulse width. Apply. So then V20 we have to give enable DC pulse the function and we'll give zero point 0.8 period will be 40 nano, then rise time 50 pico, fall time 50 pico, pulse width will be half of 40 nano is 20 nano 50%, and yeah, that's it. I'll click on apply. Then I have to give 20 V2 V into 1. I will give pulse, voltage is zero point 0.8, period is 20, 80 nano, right? We had given how much? 40 nano there, right? So we will be giving here 80 nano, and rise time is 50 pico, fall time is 50 pico, and here the pulse width will be 40 nano. Apply, and then V into 1 is done. V in 30 we should be giving V in 30 and pulse zero point 0.8 and period is 160 nano, rise time 50 pico, fall time 50 pico, pulse width will be 80 nano. In fact, you can just skip giving pulse width also. It will by default it will be pulse width will be 50% only. You need not provide. If it is other than 50% only, you need to provide. I have just a habit of giving the pulse width also, so it does not make any difference even if you don't give the pulse width. It will be by default 50% uh, of the period pulse width will be okay. So and then I will click on apply. Then I have to give it for Win31 enabled pulse zero point 0.8 period will be what? 320 nano, and then you have rise time 50 pico, fall time 50 pico, and pulse which will be 160 nano, right? Apply. So now I will just have a look at all the voltages. VDD is 0 point 0.8, VSS is grounded, then I have V in 0, 10 nano, 40, V in, uh, V in 11 is 20 nano, V in 20 is 40 nano, 21 is 80 nano. It is just doubling than the previous bit, right? Previous lower bit. Then we have V in 30, 160 nano and V in 31. Then I will click on OK. Right now, what I will do is I will just need to run the simulations. So the simulation has started. So you have the waveforms. Okay, so you can see all the waveforms are proper or not. Uh, okay, so I just wanted my output to come here. I can just drag it. Okay, I can also do that, or I can just keep my output waveform here. So So you can see that 5 nanoseconds why I gave extra is for this reason. So now you can check the functionality, right? Whether you are getting proper voltage or not. You will be able to see whether you are getting proper waveform or not. You will be able to see that. Just for one or two input combinations, we can do that. So for all zeros, it should be zero. All zeros will be what? 0, 0, 0. Will be one when all the inputs are zeros here. The output of AND gates will be 0 and the output of NOR gate will be 1. So for all 0, it is giving 1 for you. So this is proper. And similarly, for all 1, it will be 0, 0, 0. Even if it is at least one input is 1, then output will be 0. So even if at least one input is 1, you can see here, then the output is 0. Yeah, here you can see there will be at least one input is 1, then you are having that 0. So yeah, this is how you do transient simulation for a multi-input gate. Uh, okay, that's all for this video.